In this video, we're going to talk about applications of the second derivative and points of inflection. So we're going to start with number 61 here. And it tells us that the function r equals 1 over 50,000 times 600 x squared minus x cubed is defined on the interval from 0 less than or equal to x less than or equal to 400 is our revenue equation. And we want to find the point of diminishing returns. So we're going to find the second derivative of r. So that's going to be 1 over 50,000 times 1200 x minus 3x squared. And then r double prime is going to be 1 over 50,000 times 1200 minus 6x. And we're going to set that equal to 0. 1200 minus 6x equals 0. 6x equals 1200. X equals 200, which is right there within range of 0 to 400. So when we go ahead and stick in 200 now into our revenue equation, get 600 times 200 squared minus 200 cubed. Oh, I want to pull out that 200 squared. Right? That's going to give me 200 goes into 50,000, 250 times. Still got a 200 up here. I also have a 400 here. So I have 200 is equal to 0, 0, 0, 0, 8 over 250. This is r of 200 is equal to 8 times 80 times 1,000 divided by 250. 250 goes into 1,000 4 times. 4 times 80 is 320. So my point of diminishing returns is 220. Let's go ahead and look now at number 63. Consider a college student that works from 7 p.m. to 11 p.m. assembling mechanical components. The number capital N of components assembled after lowercase t hours is given by the function. At what time is the student assembling components at the greatest rate? So 63 capital N was negative 0.12 t cubed plus 0.54 t squared plus 8.22 t. This is the same question as where's the point of diminishing returns, because after that time, the rate at which the slope is that's the greatest slope, and it's going to start, even though it might be positive after that, it's going to decrease. So let's go ahead and figure out n prime here is negative 0.36 t squared plus 1.08 t plus 8.22, and n double prime is negative 0.72 t plus 1.08, and I would like to make this a negative 1 over 100, 72 t plus 108. I see a common factor of 9. 8t plus 12. That still has 4 that comes. 4 goes into 125 times. 2t plus 3. Right? So then let's see here, 8 negative 2. This will be negative, negative, and negative. So when I set that equal to 0, 2t minus 3 is equal to 0. 2t is equal to 3. T is equal to 3 halves, which is 1.5. So after 1.5 hours, and the college students started at 7 p.m. So 7 p.m. is 1900 hours plus 1 hour and 30 minutes. It's going to be 20:30 or 8:30 p.m. I prefer to work that in military time if I 24-hour time if I need to. Just helps me make sure I AM and my PM straight. All right. Let's look at number 69. This is the average cost problem that I referenced at the end of the last video. This will be our last one for this section. The total cost in dollars of operating a factory is C is equal to 0.5x squared plus 10x plus 7,200, where the number where x is the number of units produced. At what level of production will the average cost per unit be minimized? So C bar, the average cost, is equal to C divided by x is equal to 0.5x plus 10, 7,200x to the negative first. So C bar prime is equal to 0.5 minus 7,200x to the negative second. Since we're using second derivatives here, let's first find these critical numbers by setting this to 0. Give me just a second. So 0.5x squared minus 7,200 over x squared. I want to multiply by 2 to get rid of that fraction. 2 over 2. And 7,200, that is 14,400. All right. So critical numbers are x is equal to the square root of 14400, or x is equal to negative square root of 14400. X can't be negative. X is going to be the square root of 144 times the square root of 100 is 12 times 10 is 120. Let's go ahead and see with derivative now. C bar double prime is equal to positive 14400, x to the negative third is equal to 14400 over x to the third. And so then I'm interested in, there's a vertical asymptote here for C bar double prime at x equals 0. To the left of it, it's negative and concave down. To the right of it, it's positive and concave up. And I'm only interested in the part to the right because x needs to be a positive number. And 120 is somewhere over here in this area, concave up. That means that there's a local min. Of C bar at x is equal to 120. So let's find C bar of 120 is going to be 0.5 times 120 plus 10 plus 7,200 over x, which is over 120. So that equals 60 plus 10 plus another 60 is 130. So we have production level that minimizes average cost is 130 units. C bar minimum is 120 units is $130 per unit. This is average cost per unit. I might just want to say minimum for x C bar x is equal to 120 and $130. All right, that's it for this section for 3.3. We'll come back next time and we'll start talking about 3.4, which is optimization problems. So you'll need to know your some formulas here. Kind of just gave you an idea of maximizing and minimizing revenue and cost and profit and things like that. We may also might also get into some geometry problems. It looks like we're going to stick mostly to business applications, which I like for this class. The other problems are there in your textbook if you're interested in them, but they're more usually for calculus with analytic geometry, and we're interested in applied calculus here. So we'll stick to the applications that are for economics and business and maybe a little bit with applied sciences and things like that. So come back next time. There's probably only going to be one video for the next section. So come back for that video next time. See you for the next video.